Hi, welcome back to Calculus. Today we're looking at section 10.2 and we're going to do calculus with parametric curves. So in the last video that we saw, we looked at parametric curves and what they were and how to work with them a little bit. Now we get to do the calculus. So turns out derivatives especially are relatively straightforward. So let's start there. We'll do an integration problem on the next board and it will be fun. So when we talk about derivatives here, we're still thinking, you can still think of these, the derivative as being slopes of tangent lines. But we are in an xy plane for these curves. So the derivative of y with respect to x, which would be the slope of the tangent lines of the curve, is going to be dy dt over dx dt. We just take the two derivatives separately and do some division. The second derivative is a little bit strange because the second derivative of y with respect to x is the second derivative of y with respect to t, but it's actually divided by just dx dt. It turns out that it's a chain rule, and so I'm going to make you take my word for it, but it does work out that way. So if you want the second derivative, you need the second derivative of y with respect to t, but you only need the first derivative of x. All right. So let's do this lovely little problem that takes up all this space. It's actually not bad. Anyway, let's do it. Find the tangent line to the curve x equals sine t, y equals cosine t at the point, square root of 3 over 2, 1/2, and when t is pi over 3. So you can see the first thing I did is I just went ahead and took those two derivatives of x and y. dx dt is derivative of sine is cosine, and for cosine, its derivative is negative sine. So once I had those, I put them together to get dy dx. Negative sine over cosine is just negative tangent. And since we're looking at a t value of pi over 3, I plugged in pi over 3. And as long as you trust me, when you plug in pi over 3 to tangent, you get, in this case, the negative square root of 3 over 3. The negative, of course, because we had a negative in front of the tangent. So there's the slope of my tangent line. All that's left then is to put it into the form of an equation for the line. And since very conveniently we have this point, square root of 3 over 2, 1/2. You get this in point slope form. Y minus 1/2 is equal to negative square root of 3 over 3. There's that slope again, times x minus the square root of 3 over 2. So there you go. That's tangent lines with parametrics. Not too bad. Next up, we're going to do a little bit of integration. This one's going to be a little messy. It'll be fun, so hang on. Okay, so here's our integration problem, and it's so big I'm going to have to move the computer so you can see the end of it. So let's get started. Find the area enclosed by the y-axis in the curve given by t. X is equal to t minus t squared. Y is 1 plus e to the negative t. So to start with, I just wanted to see what this looked like. And so I plugged in 0, 1 for t, and very conveniently, they both gave me x values of 0. That's important because we're bordered by the y-axis here. So they both give me x values of 0, and you can see the y values they gave me. And so what we end up with is this little loop here, and very, very importantly, it is going that direction. Okay, that's going to play a really big little bit here. It really threw me for a loop for a couple minutes. So what we have essentially is we have an integral from 1 plus 1 over e to 2. So I'm treating of x dy. So we're integrating these x values with respect to y because we're going vertical here. All right. So these endpoints are 0 and are. So here's where I got into a problem. 1 plus 1 over e is when t is 1, and 2 is when t is 0. So I did the opposite of the integral from 0 to 1, because that's really nice, of all the way. And then for x, I used what x is, t minus t squared. For dy, I just had to take the derivative of y, which was negative e to the negative t dt. So then you can see, and let's start sliding. Let's slide this over some now. There, I think you can see the rest of it now, even if it's crooked. So then you can see I did all this integration. And it turns out I had to do integration by parts twice. So you can see here, for the first integration, right here, I let u be t minus t squared, which meant that du was 1 minus 2t, v was e to the negative, or I'm sorry, dv was negative e to the negative t, which meant that v was just e to the negative t. So that whole integral then was equal to t minus t squared, e to the negative t, minus the integral of e to the negative t times 1 minus 2t dt. Unfortunately, I had to go back and put a negative sign in because I had the order wrong through the whole thing. So I just threw a negative sign in front too because I had the order backwards. Then I had to do integration by parts again. So this time I let u be that 1 minus 2t, which means du is negative 2 dt, and dv was e to the negative t, which means v is e to the negative t, negative e to the negative t. So I wrote out the integration by parts. We have t minus t squared e to the negative t. That was left over from before. Be careful with this minus sign. So I have minus u times v, the new u and v that I just found. And then it should be minus the integral, but again, with that minus that we had before, now it's a plus the integral of e to the negative t times negative 2 dt. Still with that extra negative in front. Would have been easier probably just to have done it from 1 to 0 instead of 0 to 1. That would have been so much better. All right. Anyway, so all of that works out to give me this. I still have that t minus t squared e to the negative t. The two negatives make a plus, 1 minus 2t e to the negative t, and then this integral works out to be minus 2 e to the negative t. And all of that is evaluated from 0 to 1, and of course I have the negative in front of it. Long story short, when you plug in 0 and 1, this, with that extra negative that I had to put in because I did the integration backwards, you get 0.1. So it's pretty fun. That one was a mess. But the idea is pretty straightforward. We're really integrating x dy. Okay, and then we put in our parametric function for x, and we put in the derivative of y for the dy, and that then gives us something to integrate that just has t in it. So it was a big, ugly, messy one, but it worked. So there you go. Have a wonderful day.